Hello, hello.
Hello.
Hey, everyone. How's everyone today?
Good.
All right, we have 13
Good.
people already, and we're still 1 minute away from the official time. That's great. Super exciting. Let's give it a minute for other people to join, and we'll kick it off. And Sukhvinder, you're here, right? Yes, I can see you. Awesome. Let's try if you can share your screen. I assume you...
Host disabled participants can share.
Let me try from another account and I'll enable that. I'll be right back. All right. Sukhvinder, can you try to share your screen?
Sure.
You should be able to. All right. Thanks everyone for jumping in today. We're gonna kick off with Sukhvinder giving a presentation and kind of more of the medical context for us to truly understand what we need to do as data scientists and how the data science can be applied in here in the context of the computer vision model. So I'll pass the mic to you, Sukhvinder.
Sure. Thank you. Thank you, everyone, for giving me an opportunity to present at least what is pulmonary fibrosis from my point of view. I'm a researcher, so I'm presenting it from the investigational point of view. And so let's start from pulmonary fibrosis. Pulmonary means lung, fibrosis means scarring. If there is a scarring of lung over any place in the lung, we call it pulmonary fibrosis. So in today's talk, please feel free to stop me anytime if you have any question or any discussion point. So I talk about what is pulmonary fibrosis, what are the cause and classification of pulmonary fibrosis, how do we test and monitor pulmonary fibrosis, how the patient comes to the clinic, and what are the challenges in the field, and why do we need computer visions, what have been done in the computer vision, what people have tried, so and what we can do. So these would be the topics of today's discussion. So if you think about our lung, so in our lung, you can think the lung as a tree-based system. Instead of top-down, bottom-up approach, we can think that our lung is a top-down. So the air comes from the trachea, and then it goes to the bronchi, and then it goes to the bronchioles. Bronchioles are nothing but the air sacs, and then there are alveoli. Alveoli, you can just imagine, I'm just putting an imaginative lookup, that they are air sacs. They are like balloons, which can take the air. Once they take the air, they spread out. So there is a capillary. So what happens in these air sacs? So our blood, which is having lot of carbon dioxide, comes to these air sacs, and since we have sucked in the air or oxygen from outside, that air get exchanged, that oxygen get exchanged, and our blood gets purified on the oxygen level. So what happens that these air sacs are normally in the open space. And so that since they are kind of balloon, they have to spread out. So this open space helps them to spread out. And if you see, if we cut a 5-micron sections, let's say I cut it from here, a 5-micron, a very thin section of this, they will look like this. And this is a histology of that this is an air sac, and this air sac is lined by some cells, which we call epithelial cells. And if we look it very carefully, this gives us an appearance of honeycomb kind of structure. So what happens during fibrosis? Fibrosis means fibrous tissue. So this air space, one thing which happens, that this empty space of the lung, which is normally doesn't have so many cells or so many structures, is get occupied by the fiber kind of tissues, fibrous tissue. So elasticity, normally these capillary or these alveoli are highly elastic. They can be like a big structure. We can take as much as 5 liters of the air one time, and these can spread. But now they are not anymore elastic. So, and second thing which is happening, that this layer, this epithelial layer, or these cells, they start getting restructured. There is a problem that they get dismantled or damaged, and in order to remove this damage, fibrous tissue comes and occupies this area. And you can see this structure at the pathological level turns out to be this. So here is the fibrous tissue, and at the same time we have a damaged tissue over here. So ultimately there is a loss of elasticity. And when I say loss of elasticity, can I say loss of lung function? We cannot take in, so we cannot breathe out properly as much as we can do under normal condition. So fibrosis means scarring of lung tissue. So according to the Mayo Clinics, this definition I have taken from the Mayo Clinics, pulmonary fibrosis is a lung disease that occurs when lung tissue becomes damaged and scarred. This thick structure, stiff tissue, make it more difficult for your lungs to work properly. As pulmonary fibrosis worsens, you become progressively more short of breath. So symptoms, if you are saying that shortness of breath is the key symptoms of this disease. So this is our healthy lung. This is our damage of fibrotic lung. So there are multiple factors which are coming up. So these alveoli, now they want to get enlarged because they want to take more air. The body make it in such a way that they get enlarged. So which I will show how that looks like in the images. Then there is a fibrous tissue, which leads to honeycomb kind of pattern. And at the same time, these bronchioles, they get more stiff and they get extended out. So there are multiple features. So when we will be looking into the images, we will be looking into the characteristic like honeycomb pattern. We will be looking into bronchistasis, where the bronchi are big and enlarged. And at the same time, we will be looking into this alternative pattern where normal lung is affected by a fibrotic lung. And these would be the features which we will be considering while thinking into the imaging of these features. So at functional level, what is happening? We can take easily, normally we can take a lot of oxygen very easily, but in the fibrotic lungs, lung expands poorly and less oxygen enters into our blood. When less oxygen enter into our blood, our heart start pumping more. It has under the pressure, so that because it is not getting the oxygen, the required oxygen, so we get hypertension in that regard. And at the same time, and many of the body organs start getting affected, and you can clearly see. So at functionally, when we work, what we observe cough, we observe fatigue, dizziness, shortness. When I talk dyspnea, I'm talking about shortness of breath. So this is the percentage patient, which are different patient observe these kind of symptoms, and then they go to the clinicians, then they go to the physician, and then they try to dig out what is happening. So clubbing is what one thing is that because of less oxygen, your fingers get club shaped. At the same time, so these symptoms are in the patient lead them to the clinicians or the physician to figure out what exactly is happening. And when we start thinking about symptoms, we start thinking about the cause. So what has caused this fibrosis? This fibrosis, which is happening in the lung, it can be age dependent. It can be occupation dependent, like we are introduced to chemicals at our occupational space. That it can be genetic, that some genes from our parents has come to us. At the same time, sometimes we take some drugs, and that drugs can cause this fibrosis. And in addition to all this, many times you get some medications, and those medications also cause it. So this is from the challenge. This whole thing I have taken from the challenge. Pulmonary fibrosis experts, the one thing they all agree is on that this disease is heterogeneous. It's not just one formula for this disease. Many factors can cause it. We can get many kind of differential imaging. At the same time, we can get different disease progression rate also. So pulmonary fibrosis is not a single disease, it's an umbrella term. So there are thousands of diseases which comes to the pulmonary fibrosis. And the result is that our lung functioning has somewhere hampered. So that is the key criteria for pulmonary fibrosis. So, so these are the diseases. So sometimes we can figure out the cause, like so why we want to know the cause. If we know the cause, we can remove that cause. Let's say some medication caused the fibrosis. We'll remove that medication from our diet, and we can be better. Or occupation caused it. We will not be getting introduced to asbestos or some chemical which has caused pulmonary fibrosis. So one thing is, if we know the cause, we can take care of it. But many times what happens, we are unable to know the cause. So then it becomes idiopathic pulmonary fibrosis. That is pulmonary fibrosis of unknown cause. So, and then there are some diseases like sarcoidosis, other diseases which are coming up together and which makes this disease pulmonary fibrosis. So now I've talked about what is pulmonary fibrosis, what causes it, what are the symptoms, but how do we diagnose it? When we go to the clinician, when we go to the physician, what he looks into are, how he figure out that what stage we are at pulmonary fibrosis, and do we need to give some therapies? What kind of therapies need to be given? Or do we need, so that is signs and symptoms are done. They go for the lung function test. What is lung function test? So lung, mainly the main role of the lung is to inhale the air and exhale the air. So they try to look into this thing which we call it. Okay, so before going to lung function test, what causes pulmonary fibrosis? Age can be the causative. Older the patient, higher is the tendency to fibrosis. Over the timing, our cells start getting damaged. Damaged cells are replaced by the fibrotic tissue. Fibrotic tissue leads to fibrosis. So age is one of the factors. More in men than in women. Smoking is the key factor. The inhalant of the smoke can cause fibrosis, and then that cause be the cause. And sometimes it comes in the ex-smokers with age also. Occupation, cancer can be the cause, genetic factor be the cause, family history can be the cause. So how we diagnose it? So I was talking about the lung function test. So in the lung function test, what they do they do spirometry. Spirometry means measurement. So spirometry is the measurement of breathing. So what happens that they ask you to breathe in forcefully. So that is a forced vital capacity. And in our this challenge, forced vital capacity is the key. So they are asking us to assess this forced vital capacity. So once we have taken the air, so with the force, how much air we can exhale. So how much you exhale and how quickly you exhale. These are the two key criteria for spirometry. So spiro, it's a Latin word which means measurement of breathing, and three criteria: how much you inhale, how much you exhale, how quickly you exhale. Normally, this goes here like this. So normally we have, this is the time dependent, and this time is from 1 second to 5 seconds, and this volume is still 5 liter. This is a 5 liter capacity. So what happens in normal conditions? We have this. In obstructive means either it can be restrictive or it can be obstructive. Restrictive means mucus is much, cough with the phlegm is in your lung. But normally fibrosis, which we are talking about, idiopathic pulmonary fibrosis or other fibrosis, they comes to the obstructive, where lung function stop up to the optimal. So forced vital capacity is the measurement. So in that, and they try to measure how much air can be exhaled. And the aim of this competition is to predict the patient's severity or decline in the lung function based on a CT scan of their lungs, as well as their functional test, which is forced vital capacity. That is the volume of air exhaled. So in the present, we need to predict that can from HRCT images or other meta-markers, can we predict forced vital capacity of the air? So once what happens in the diagnosis, you are suspecting something, go to the spirometer. You identified that there is autoimmune disease, exposure on medication. Yes, there is something which is causing this fibrotic lung, and they go for and take your high resolution contrast tomography, that is HRCT image, and then there is a discussion panel, multidisciplinary discussion panel. So where a physician comes into it, a radiologist comes into the picture who looks these images day-to-day basis, and a pathologist comes into the picture. And they, based on the person's symptoms, history, physiology, functional test, that is spirometry, they makes the discussion. They figure out whether it is we know the cause or we don't know the cause. If they don't know the cause, they call it idiopathic, means unknown cause pulmonary fibrosis. And if there is some reasons they are not able to figure out whether there's a pulmonary fibrosis, what they do, they take a bronchoscope. Bronchoscope takes is a pipe, and that pipe goes into your mouth, into the lung, and then they take small tissue from the lung, and then they do this kind of scanning. This is 5 micron. So this is millimeters, this is microns. So that is what they do. So after that, I was talking about FVC, that is forced vital capacity. What happens, why forced vital capacity is so important? Yes, it's a functional test of lung, but at the same time, why we need that? It has been observed that functionally stable patient, sometimes these patients survive 4 or 5 years. They have worst prognosis. When I say prognosis, it means the tendency to survive, how long they survive, how long they live. So functionally stable patients show decline in FVC of a maximum 5% in 6 to 12 months. So today patient came up, he has difficulty in breathing, dizziness or other symptoms. But 6 to 12 months, the capacity to forced exhaling of the air is just declined by 5%. But If there is a decline of 5 to 10 percentage point, that there is a progression of the disease. Means disease, now your FVC capacity is decreasing more. Means there is a higher decline in that percentage. If there is a decline which is more than 10%, or in 6 months, it is associated with 4 to 8-fold increased risk of death in the next 12 months. So it means your lung function is deteriorating at very high pace. So that is, and sometimes which we need to keep in this challenge. That is why I'm bringing the acute exacerbations into the point. Sometimes initial lung scans would be really good because they have given us multiple scans of the HRCT. Initial scans would be good, but there would be one scan where there would be some activity in the lung. And that scan become the key, because sometimes what is happening in the body, we don't know. Some trigger is there, and this fibrosis has gone to the extreme, severity has increased, and they call it acute exacerbation. I'll read this line. In this acute exacerbation are important aspect of the clinical progression of pulmonary fibrosis. These are characterized by increase in the shortness of breath over a period of 30 days. And high resolution HRCT show new infiltration of the lungs. So there's something new coming into the lungs, which we may be knowing, which might not be knowing, but there is a frequency that 5 to 15% the chance that you will get this kind of acute exacerbation. And if there is acute exacerbation, patient die within 3 months. So it's a very bad disease. So very bad stage. Might be initially our scans are very clear. We got one image at one particular time point, that would be a click. So what is HRCT? So that is, okay, lung function test has been done. We know that some problem is in the lung. But over the time being, advancement in the imaging has been done. So they take CT images of the lung. So in this HRCT, HR stands for high resolution, and the CT contrast tomography. So they take very thin slices of the lung. So they take longitudinal also, they take axial also. So in these axial images, they try to look what are these axial images look like. So this is our lung only, and we can take these images which has been provided, DICOM images which are everywhere. So this is a diagnostic test. So in this diagnostic test, what happens, it allows us to diagnose the disease, but it doesn't help us to prognose the disease. So ultimately, it is an image of our lung. This image can help us to predict how the disease is going to go. It's gonna go bad or it's gonna go good. If it's gonna too bad, can we go for heart transplantation? Or if this medication is giving us a problem. Hello. So this is the challenge which we need to take care. So this is the diagnostic imaging. Idea is to make this diagnostic image to prognostic image. We can predict the disease severity as well. We can predict how it will be 10 days down the lane or 1 month down the lane. That prediction need to be done, and that is somewhere this challenge is addressing. Yeah.
If I may ask, this image on the top, on the bottom right, is the same CT scan but just different color map?
No, I'll show you a different color map. This is, so what happens, this is non-contrast, this is contrast. In this, they ask you to drink the contrast. You will drink the contrast, and then they will take this contrast image. But at the same time, I'll talk about that. I have one slide on that. So now this image you take, this is a normal lung. You can clearly see there is dark, more darker it is, better it will be. And these are the reticulations where we are seeing the trachea, we are seeing the vessels. What happens, these cysts, these things which alveoli, their layer become very thick. The moment, because they are losing their elasticity, they are getting thickening. So these thickening appears like a honeycomb pattern. Honeycomb, we can visualize. Normal lung don't have it, but this lung has it. There you can see. So radiologically, honeycombing is characterized by clustered cystic layer spaces, cyst of comparable diameter. Means we have small cyst kind of structure which are about or less than 10 millimeter. So this pattern is one thing which they look into. Now I'll talk about other patterns also. So in addition, so if this is a lung taken out, this was just a scan, axial scan, but at the same time, sometimes from the old patients, some from the autopsy patients, they took the lung, then they took the whole tissue and they assess it. And this is how this feature looks like. This is one that we need to look this honeycomb pattern, this kind of combing pattern. At the same time, in addition to these trachea, this bronchitis, these bronchioles, they normally they have a elasticity and they are of particular size. But at the same time, what happens in fibrosis? They become thick, they become extended. They want to take more and more air. They want to inhale more. Their capacity is that, and that reticulum. So that thickness in normal lung you won't see like that. In normal lung you will see, because these are axial images, you will see the tree coming up, tree branches coming out, but they won't be that thick. So that thickness comes up. They call it bronchistasis. Now they have started defining that bronchistasis can be of cylindrical shape. Bronchistasis can be varicose, where this branch, we can say terminal leaf branch, divided into two, or they can be of cystic type, right? So that is what they talk about. Then they talk about ground glass opacities. So ground glass opacity means it's a radiological finding. There you will look like a white sheet on the lung, and that white sheet it gives a hazy look what is inside the lung. It's not so a radiological finding is in the computer consisting of hazy opacity that doesn't obscure the underlying bronchial structure or pulmonary vessel. So I have talked about certain points which are very important, but they look for patterns like reticular pattern, nodular, high attenuation, low attenuation, that is ground glass opacity. They also look whether it is in the top of the lung, bottom of the lung, in the anterior or posterior, in which part of the lung it is. At the same time, they talk about that whether it is in this lobule, which lobule is there. So basic interpretation is, what is the HR pattern? Is it reticular? Is it nodular? It has high attenuation or it has a low attenuation? Or it is which part of the lung? Is there upper versus lower? And what exactly sometimes fluid get accommodated. We call it clear fluid. I can talk about that, but I have not put it here. But that comes up. So there are multiple factors. That's why we call it heterogeneous as well. So high resolution, so I talked about HRCT. So high resolution computed tomography play a central role in diagnosing pulmonary fibrosis. It has been said that a good and expert radiologist can with 95% surety, with 95% confidence, can tell whether it's a pulmonary fibrosis or not, what is the stage of it, if he's very experienced. That is the human eye experience for this. And they want to use this experience, can we do with imaging? With AI or with computer vision? Can we come up with the same kind of accuracy or not? So now the metrics are not just HRCT based. They include gender, they include age, they include physiological functional, that is spirometry, in which forced volume, FVC, forced volume capacity, and sometimes they take diffusing capacity of carbon monoxide, which they call it DLCO. They take into all those accounts, and they are coming up with the metrics. But at the same time, they are sure, clinician, physician are sure only in 50% of the cases. In other 50% of the cases, they don't know. What has been done, these are very recent articles where the computer vision has started venturing into these things. Up to now, mainly it was a manual thing, but at the same time now automation has started coming up. Why automation? What is the need? They need automation. So somewhere they want to reduce the human labor. They don't want, somewhere they want to get more accuracy. Somewhere they have features, but since it is mainly the system is not that sophisticated, those systems are unable to calculate. So in these articles, which are very recent articles, so I wanted to see what is the computer vision, what they are doing, what has been done. That is why I searched the literature and I got into this point. In this paper, it was Journal of Clinical Medicine, appeared just in 2019. In this, they made slow progressor and rapid progressor. We know that rapid progressor will be dying very fast. And they just took two scores, ground glass opacity, which they called it alveolar score, and fibrotic score. And they saw that when there is a ground glass opacity, the progression is rapid. And you can clearly see from here to here, p-value is significant, and then they see clear trend that yes, but at the same time, the other score didn't give that much in this case. So in case of slow progressor, that change was not there. Somewhere they told us that HRCT, alveolar and interstitial scores were assessed and correlated with forced vital capacity. And these were longitudinal. When I say longitudinal, I've taken HRCT taken after 1 month or 3 month or 6 month difference, and they have also provided us it. And then this is another article. There they looked into the fibrotic score. This is the image which is computation. You asked me the question, and here they have used our program, and in that they made this contrast images by them. And this is a fibrous area. Here they wanted to see that whether fibrosis is, it's another article, same 2018 published recent article. They are saying that fibrotic score can assess as performance of pulmonary function. And in this, they interclass correlation coefficient, and they did data-driven texture analysis. And in this data-driven texture analysis, they contrasted the fibrotic area. And then they associated this fibrotic area with what we call lung function test, that is FVC. And they observed that there is a very strong correlation. That is a mean change in DTA score with 95% confidence, 9.1. According to, I'm using their wording, not even my wording. So interclass correlation coefficient for baseline and follow-up DTA score in each subgroup of stable subject range from 0.78 to 0.91, showing good to excellent reliability of the DTA. So, and over the timing, they could see that significant difference. This is another article. Again, this appeared in very recently, I think it was 2018. And in this, they are predicting outcome of idiopathic. When there is, many research has been done on idiopathic pulmonary fibrosis because the cause is unknown. Because cause is unknown, severity goes very high, very fast. We want to know why. We want to take away that cause. So, and it is long run. It is not that if the cause is not known now, it won't be known now 6 months down the lane. Sometimes patient history and patients start experiencing that what is causing it. They start looking into it, and then patient goes from IPF to normal pulmonary fibrosis where the cause is known. But majority of the research which I feel is done in idiopathic pulmonary fibrosis where cause is unknown. And there they have done ACD, automated computer tomographic analysis. So here they wanted to see their major score was vessel related structure. Vessels are blood vessels, capillary, because they also get extended. So they made the contrast here. They took the CT images, normal CT images, used the algorithms, which they call it Caliper, computer aided lung informatics for pathology, evaluation and rating software. And they did, because under to human eye, we cannot count these structures. But using this Caliper method, they counted it. And once they counted it, they try to say that vessel-related structure. Does this vessel-related structures can predict outcome, can predict prognosis, can predict lung function test or not? That is what they wanted to do. So vessel-related structure can better predict functional decline and survival in IPF and reduce requisite sample size in drug trial population. There it was so now, since if you don't know this, if you don't have good functional test and good HRCT test, what happens? You have to take a lot more patients to predict the therapeutic outcome. So their goal was that they wanted to have better therapeutic management. So they thought like this kind of automated system can be better. So, and if I conclude it, they say that VRS score identify patient in whom antifibrotic medication prolong life and reduce FVC decline. So there they were trying to predict the therapeutic outcome. But here also, vessel-related structures which were not achieved by the human eye, which were not quantified by the human eye, and which were beyond inter-observer bias, because one radiologist might be counting, one clinician might be looking like this, and another might be looking at another way. So this score has turned out to be better. So then in the same article, they have compared the caliper to gender, age, physiological function test, visual scoring. I think PFT stands for, I can tell you later. So they associated it. Here they have discovery set, they have validation set. They just measured the significance of this, minus log 10p. So negative log of p-value. So means positive is a good indicator. And there also they have find that caliper is good. Caliper is giving us very good values. So computer aided diagnosis is getting better, though they just measured one parameter. They didn't even go into the deep learning. They didn't even assess. They just counted the vessels. So this is another paper. Here now they have used better modeling. Here what they have done, they have used different kind of filters. So they have done tissue characterization. They have done anatomy segmentation. So in this paper, what they have done, in this paper, they have taken lung partitioning in 12 regions, from left to right, craniocordial. So because the DICOM image provided in this challenge are from cranial to caudal. Cranial means head, caudal means tail. So from tail to head means from down to upper part of the lung. Central peripheral splitting they have done so that they can see everything and their intersections. So which part of the lung? So they have taken healthy lungs where there is more black. We can see some septa, but not that much. Then they have taken into account filter for ground glass opacity. They have taken the filter for micronodules. They have taken the filter of consolidation, which is totally opposite of ground glass opacity. Then the reticulations, how we can see these capillary networks and all, and as well as honeycomb pattern. And they are telling that computer-aided detection algorithms are as good as a physician, and somewhere the accuracy has been better from the radiologist in figuring out the disease. So here the system is going towards automation. They want to assess how good it is. So in another one, so this paper I couldn't download because I have requested this paper. Here they have used convolution neural network. And in this convolution neural network, they are using deep learning algorithms. And in that, they are concluding that CNN accuracy was 76.3%, outperforming 51 of 91 thoracic radiologists. They have the data from 91 radiologists. They have used so much gold standard. And their CNN is turning out to be better in diagnosing or in classifying fibrotic lung disease on high resolution computed tomography. So with that, I will say that when I am reading this literature from an observer point of view, we need to have meta-marker panel where we cannot exclude gender, age. We should include gender, age, or functional test. We should have deep learning feature and regression models. Sometimes they take learning features and make a regression model where accuracy or AUC keep on increasing over time. Here we have not asked AUC, but at the same time, if we need to improve 95% confidence interval. Sometimes subclass in patient population, we need to take into account that every patient might not be same, that one feature might not be suitable for all. There might be subgroup where one feature is predominant, the other feature might be predominant. Filter selection has to be careful, and we need to make multiple filters. Might be one turn out to be better, and might be we will be coming up with a filter which is not even there, which can be better. Longitudinal follow-up, look out. We need to carefully look out that might be there is acute exacerbations. One time there is something coming up which was not earlier, which was not later on, but that acute exacerbation can help us in predicting our FVC as well as predicting the survival. So one thing, they have given us cranial to caudal images. They have given us full lung scans. So when I was reading what is the significance of cranial to caudal, the terminology they ask about it is that they want to go for propeller blade distribution. This variant gets its name from the fact that when seen on a sequential axial images from caudal to cranial, the honeycombing or reticulation changes. Sometimes it's in the one part of the lung, or sometimes it is in the interior part of the lung, or sometimes it is in the posterior part of the lung. Thank you. That's all from me. Any questions?
All right. I mean, that was a lot of information. We'll probably have to spend some more time digesting it after the call. But thank you so much. Very insightful, and definitely gives way more understanding on the actual kind of like applied tasks that we'll be working on. Maybe Sergey, do you have any questions?
Actually, yeah, I have one question. Can you please switch to CT images from any article? It doesn't matter, but slide that will have CT images.
This one?
Maybe another one, because this is segmented. Yes, so what I wanted to ask is, what is the window used here? Is it, oh, this one is good. Is it a standard lung CT window?
Yeah, it is. I think it is 10 millimeter or less than 10 millimeter. I can be making sure. This. Mm-hmm.
Yeah, I would like to ask you if you can check this. I mean, in terms of house field units,
Okay.
what is
I understand.
range?
Yeah, so I understand your question, and why this question came to his mind is that when we are taking the scans, very thin slices, so one at one particular place and at one particular scan, we can get the feature which we are requiring it, and might be if we make it too thick or maybe making it too thin, it might be problematic. So yes, I got your question and I can answer you that. I can see into the literature also.
So I think there are two things. First thing is first thing is thickness of the slices, and then another thing is like I think it's called histogram normalization or something like this. Is when you have an image.
Yeah.
Sorry.
G-stack?
I'm not sure. It's when you adjust the colors, because with some window you can investigate, you can look at bones, and some some CT window you have a much better view at alveoli and bronchioles, you know. And I know there is such thing as CT window. You usually radiologists will adjust this, and
so here
have a better view.
Yeah, here there is a point. So when they were taking into the point, so they were saying that they have taken one image from here, one image from here, and one image from here. So from here, from here, from here. So even if I think they came up with a 12 feature scan based on this. I can share these articles with you, and at the same time, I can also look into it.
Okay, thank you.
Can I ask a question about this paper?
Yeah, you can. I have just read it. I have not read it for defending point of view, but I can.
Well,
Yeah.
do you think that in the conclusion of this paper that there was a difference in the region of the lung and the usefulness of the findings? For example, in figure 3, are the caudal portions, the apical portions of the lung, less useful in determining the diagnosis of pulmonary fibrosis compared to the caudal lower, those sort of magenta colored sections?
Yeah. So I can pull out this paper. Let me share the paper. But at the same, so this was more mathematical paper. So where they want to use that, okay, exactly what, but I think that answer would come from the paper pulling. Pull out the paper. because they didn't venture into. Okay, let me share my paper with you.
The reason that I asked the question is I wonder if the fibrosis occurs more predominantly in the lower lung fields. And I wonder if it would be useful to filter the CT scans to look at the lower half of the lung images. I mean, couldn't you find the median value for the slices on the CT scan and just select the lower half? And would this be more valuable in predicting the progression of the disease as compared to the entire scan?
Yes, no, you are right. This I have not read in this article, but at the same time, I have read in other articles that particular portions are more prone. And when we are looking at the images also, many times those patterns comes into the low, like reticulation comes in the central part, but at the same time, honeycombing comes in the posterior part. So here is the paper. I was talking about, right, they have not given much details here because it was more towards a methodology paper they are talking about. I'm going to the results section.
So do you think that the purpose of this paper is to say that there are different features of pulmonary fibrosis that occur in different regions of the lung?
Yes. So this paper is trying to assess altogether different features, and does they have any correlation with it or not, or can an automated test can come up which can take into account these features.
Right. So then there might be multiple ways that you would filter the entire volume of the lung to look for particular features. And again, as opposed to looking at the entire CT scan, it might be valuable to segment the entire CT scan into different regions and apply different algorithms to different regions to look for different characteristic patterns.
Exactly. No, you're absolutely right. And that is where I feel that we need to decide our filters carefully. And no, you are absolutely right. Any other question?
Are you gonna? Can you give us the link to this paper in the chat?
What I can do, I will share all the papers which I have used. I can share. I can share all the papers because I try to get into 8 to 10 papers.
Maybe what would be helpful if you can send to Slack channel slides, the list of papers and any additional materials that would benefit us looking through them.
Okay. So, yeah,
Thank you. Anyone else? Okay.
I have one comment.
Go ahead, Randall.
Yeah, I just wanted to clarify the difference between obstructive lung disease and restrictive lung disease.
Okay, I have a slide for that.
Because there seems to be, it's easy to confuse those two conditions. And one of the critical features of restrictive lung disease is that the ability to, the main feature is that the total lung volume decreases.
Yes.
Compared to obstructive lung disease where the total lung volume increases. In restrictive lung disease, the ability to force air out very quickly in 1 second
Yes.
is not impaired very much. Actually, you can see that in the graph that you have there on the right. Restrictive lung disease, the vertical line that says FEV1 is the ability to force air out in 1 second.
Yes.
And you can see that the slope of that green line is very similar to normal.
Right.
But then the the amount of air that's in the lung that can be pushed out is less because the volume of the lung is reduced.
Right.
Whereas in obstructive lung disease, the ability to push air out is impaired significantly. So in obstructive lung disease, you can't push the air out rapidly. Your airways collapse.
Right. Because of mucus.
Yeah. So you're looking at the blue line is the forced vital capacity. That's the total volume of air that you can push out in 5 or 6 seconds. But in obstructive lung disease, the actual total volume of the lung is much increased. But it's not functional because it's not possible to exchange the air that's trapped in that big volume of lung in an obstructive patient. Whereas in a restrictive patient, he does not have an increased total volume of space in his lung. He has a sort of a shrunken, restrictive, smaller volume to work with, but he is able to push the air back and forth.
Yeah, right.
And I guess the other thing is that smoking is one of the major risk factors for obstructive lung disease. And I would imagine that if you're a smoker and you also have a condition that causes restrictive lung disease or pulmonary fibrosis, then you can have a mixed picture.
Right.
So you could have a reduced lung volume, and then in addition to that, you could also have some difficulty moving air in and out that is typical of obstructive lung disease. And so the smoker may have a more complicated picture than a person that just has pure restrictive lung disease.
No, I think the prognosis might be really, really bad.
Yeah. So if I can make one more comment, I think, what's kind of interesting to me is having recently looked at the mechanism of coronavirus infection.
Yeah, and ground glass opacities.
The appearance on the CT scan, and the idea that idiopathic pulmonary fibrosis means that there's no known cause, but it seems to me that you could imagine that a person could experience a viral infection and no one would be able to isolate the cause of that infection, and they sort of get better in the short term, but then in the long term, they develop pulmonary fibrosis. And I worry about the idea of the long-term effects of coronavirus infection in people who have mild symptoms now. But if you think about the process of the infection, for example, the young children that get the multi-inflammatory syndrome, where there's a overreaction of the autoimmune system and the release of all these inflammatory markers that cause this profound inflammation in the alveoli of the lungs. You could imagine that if that turned into a chronic process, that over years they might develop a pulmonary fibrosis. So even though they seem to have recovered in the short term now, I wonder if 5 or 10 years from now, those young children are going to experience a pulmonary fibrosis kind of chronic condition.
I think the virus can get the seed into the system, and that inflammatory seed can progress over the time unknowingly. We never know.
Okay, so I think in terms of medical part, there's a lot of things that obviously I don't understand as a person from very far from medical space. But I think we have plenty to at least start exploring the current data sets, start asking Sukhwinder and Rendell specific questions on the the type of data that we're dealing with in this current challenge, and the potential application of computer vision and different approaches to building models. I really like the suggestion of segmenting the lung into different areas and trying out different models for that. So maybe someone can take on that part of the process and kind of outline the structure of that. Maybe Sukhwinder, you would be able to create a quick, I don't know, a document or maybe a message to give more structure. And yeah, Harsh, we'll be sharing slides after this call, along with the video that will be uploaded on our YouTube channel. And it will also include links to all the papers that were mentioned.
Yes. I can share the slides as well as all the papers. And one thing I was thinking, I can go through the literature and I can come up with the filters. Which kind of filters would be useful for this?
Yeah.
So, and then, yeah, then we can make some further steps on that.
That sounds like
if you guys feel that there's something which we need to explore more, I can work out on that too. Means next presentation or in the future we can do that way too. Means these questions we need to handle now. I can take that task too. At least from the medical side, I can be, because I know this domain better in a way that I can understand these terminologies.
Can I ask another question?
Mm-hmm.
Does anyone think that gender is a independent feature that's valuable as apart from smoking?
So yeah, so I have that figure in my hair. I didn't present that figure, but so now I think this one is the one, or this one is the one. Okay, here is the point. So so the at present predictor is based on the gap. Automated computing has not come to the clinic. Everything is at the research base. Papers are being published, but not at the clinical level. Clinicians are not using it at this moment. So, but what exactly is being used at present is a gap index. In the gap index, gender, age, and physiology. Physiology means FVC as well as DLCO, that is diffusing capacity of carbon monoxide. So these two parameters are taken into account. But, and they have given the points to everything. And male gets more points because they have high risk factor. They are being considered more risk factor. And after that comes the age, and then comes the physiology. These key criteria are taken into account.
And not smoking? They don't consider smoking?
They do consider smoking, but then in this gap physiology-based score, they don't take into account. Smoking comes as a historical point, definitely, no doubt. But at the same time, if I have another scoring system, no account has been given to smoking. Yes, no.
Okay, so if you look in our database, then twice as many men are ex-smokers compared to women.
Smoking is the main culprit. If you go to the symptoms, if I have put one slide here, and smoking is the biggest factor. And if you go to the competition, if you read the language there, only one risk factor has been accounted at heavy level, that is smoking.
Right. So is the effect of being male really just a reflection? Is it just a bias that's a reflection of the fact that twice as many men are ex-smokers compared to women?
I think
it's not really gender. It's the fact that
male smoke more. Yes, I think because since they consider gender as the key criteria for the gap index, they might have done confounder based assessment, where they might remove the confinement of smoking or non-smoking. So that is why this criteria has been taken into account with heavily. So I understand your question, but I think that bias might be taken care earlier. There might be certain studies on that. Definitely, to me, look like that. So that this confinement or this confounder can be taken here, and they might have looked into the p-values where exactly the gender issue comes as a key characteristic.
So if you run the Kaggle notebook and you eliminate gender and you get the same or a better prediction, then wouldn't that imply that the gender really is not contributing to the discrimination of the notebook? It's really just smoking.
I think we have to have a separate parameter assessment with or without gender into account. So whenever we are developing this composite scoring system or a composite algorithm, I think we should take into account that how much gender is contributing or how much significant the gender has been to this better performance of the confidence for non-functional test.
So isn't a way to do that just run the notebook with gender and run it without gender?
I think yes, we can do that.
All right, we have 2 minutes left, or 1 minute left. I would like to wrap it up, and thank you, Sukhwinder, for delivering an amazing presentation. Lots of knowledge and depth that we need to digest. And I'll be posting the video on Slack channel, on our YouTube channel, and we'll wait for slides and links to papers from you whenever you have time to send those in.
Thank you.
All right, thanks everyone.
Yeah.
Bye-bye.